In the early days of generative AI, the dominant architectures, variational autoencoders and autoregressive networks, relied on a rigid statistical foundation. They optimized an explicit probability likelihood. These explicit likelihood models operate by asking a strict mathematical question. What exact probability does my network assign to the real data in the training set? But optimizing for this explicit probability forces a compromise. To avoid heavy penalties for getting a detail completely wrong, the models hedge their bets, averaging out uncertainties and producing safe, consistently blurred outputs. The Generative Adversarial Network, or GAN, took a different path by abandoning the calculation of explicit likelihoods entirely. By the late 2010s, this approach was producing the sharpest synthetic images in existence. These hyper-realistic faces, outputs of a GAN, became the standard for high-fidelity generation for several years. GANs are implicit generative models. Rather than calculating exact probability densities, they learn how to sample directly from a data distribution by playing a continuous adversarial game. The statistical objective is replaced by a much simpler question. Can anyone tell my synthetic samples apart from real data? By discarding the safety of a stable statistical target for a two-player contest, GANs achieved extraordinary image sharpness, though this introduced the structural instabilities that would eventually limit their use in large-scale applications. The basic GAN architecture pits two opposed neural networks against each other. On one side, the discriminator receives both a real and a synthetic data point, outputting a binary verdict. Crucially, a feedback loop shows the generator never actually observes the real training data. The counterfeiter learns only from the detective's reactions. The generator's entire education is derived exclusively from the gradients provided by the discriminator. Mathematically, we formalize this as a minimax objective, separating the probabilities for real and generated data. The discriminator seeks to maximize this function by assigning high probability to real data and low to generated. The generator minimizes the function by pushing the discriminator's output close to 1. Here lies the root of the architecture's core instability. Training a GAN isn't about minimizing a fixed loss curve. It is a search for an equilibrium between two constantly moving targets. When that equilibrium fails, the system breaks. If the discriminator becomes too accurate too quickly, it perfectly separates real from fake. The gradient drops to 0, and the generator stops learning entirely. Alternatively, the networks can fall into an oscillation failure, chasing each other's updates in cycles without ever actually settling. Treating generation as a dynamic equilibrium search creates hyperparameter fragility. A configuration that converges reliably in one laboratory might completely fail in another. This fragile equilibrium directly causes the most common failure state unique to the GAN architecture, mode collapse. Mode collapse occurs when the generator discovers a handful of outputs that reliably trick the discriminator, and then generates exclusively those few examples. To understand why, consider a data distribution with 8 distinct peaks. Likelihood models face mathematical penalties if they fail to cover the real training data. Because of this strict penalty, these models are mode covering, stretching their output distribution across all 8 peaks. Returning to the GAN, we see the immediate cost of abandoning explicit likelihood. The architecture possesses no penalty for ignoring the vast majority of the dataset's diversity. The generator is strictly rewarded for one thing: fooling the discriminator. Emitting one perfect counterfeit yields the exact same reward as producing 1,000 diverse ones. As a result, the GAN is mode-seeking. It can win the game by collapsing its output capacity onto a single, narrow sliver of the data, ignoring the remaining 7 peaks. The very mechanism that allowed GANs to avoid the blurring effect of explicit probability ensured they would struggle to capture the full diversity of their training sets. This mode-seeking behavior created a significant evaluation problem. If a model produces no likelihood score, researchers have no clear way to mathematically prove it is generating high-quality, diverse data. Relying solely on human visual inspection works for spotting obvious artifacts, but human reviewers cannot reliably measure dataset diversity across tens of thousands of samples. The standard solution eventually became the Fréchet inception distance, or FID. We pass both real and generated images through a pre-trained network to extract deep feature vectors, creating 2 distinct data clouds. FID models these feature sets as multivariate Gaussian bells, establishing a mean center point and a covariance spread for each. The metric then computes the distance between these two resulting bells. A lower score indicates the generated data more closely matches the real data. By measuring the shift between the means of the two distributions, FID evaluates overall image quality. And by measuring the covariance matrix, it detects diversity and mode collapse. If the generated distribution has a shrunken covariance, it mathematically indicates a lack of variety. FID became the dominant metric because it successfully captured both axes of the generative trade-off, quality and coverage, into a single quantifiable number. Around 2021, the focus of image generation research shifted as diffusion models began surpassing GANs on quality benchmarks. This shift occurred even though GANs were still generating incredibly sharp images in a single, fast-forward pass. But examining this matrix, we see why the field traded the GAN's speed for diffusion's reliability. Diffusion matched the GAN's peak visual quality while using stable, fixed-loss training. Furthermore, diffusion utilizes a likelihood-based objective, ensuring full mode coverage and solving mode collapse. GANs are not obsolete. Their architecture still thrives in specialized niches, like real-time on-device generation, where fast sampling speeds are non-negotiable. More importantly, the core idea of adversarial supervision, training one network against a learned judge, proved too useful to discard. Today, the adversarial loss is treated as a modular component. The autoencoders used in latent diffusion models rely on it to ensure their reconstructions stay crisp instead of blurry. The transition to diffusion suggests that in production environments, stability and dataset coverage are more decisive than raw speed or peak fidelity.